Hey everyone, ready for a deep dive into something really cool? Today, we're taking on LLMs. You know those large language models that are everywhere these days.
Yeah, they're pretty hard to miss.
But here's the twist. We're not looking at the usual hype. We're going to look at LLMs through a totally different lens, the lens of information retrieval.
Now that's an interesting angle.
I know, right?
Right.
It might seem kind of unexpected, but trust me, it's going to be fascinating. Our source material today is packed with some seriously cool insights.
Yeah, and even some myth busting about how we usually think about LLM training.
Okay, so how does this connection work? How do these powerful language models relate to something like, say, Google search?
Well, think about what happens when you type a query into a search engine. It sifts through tons and tons of web pages, right?
Ranking them by how relevant they are to what you searched for.
Exactly. LLMs do something very similar, but instead of web pages, they're sifting through all the possible combinations of words.
All the possible combinations. Wow, that must be a massive amount of information to process.
It is. And just like search engines use algorithms to figure out relevance, LLMs use something called encoders. They're like comparison engines, scoring how well different word sequences match the prompt.
So the LLM's prompt is like my search query, and it's trying to find the most relevant document. But the document is actually just a string of words.
You got it. And just like search engines rank those web pages, LLMs rank those word sequences by how likely they are to be the right response.
So the LLM is searching through this massive library of potential responses, just like a search engine searches the web. But instead of giving me a list of websites, it gives me a coherent piece of text.
It's pretty mind-blowing when you think about it.
It really is. And get this, the way an LLM decodes text, word by word, can actually be seen as a series of tiny retrieval steps.
Whoa, hold on. Break that down for me.
Okay, so each time the LLM picks the next word in a sequence, it's like it's retrieving the most probable document from a set of possibilities, kind of like choosing the best search result from a list. So in a way, the whole process of generating text is actually a series of information retrieval tasks happening super fast.
Precisely. And it gets even more interesting when you bring in reward models.
Reward models. Okay, I've heard that term thrown around, but remind me, what are they exactly?
Well, they're used to fine-tune LLMs to make them even better. You can think of them as like re-rankers in the world of information retrieval.
Re-rankers.
Yeah, so think about your search results again. A re-ranker takes that initial list and refines it. Make sure the most relevant results are right at the top where you see them first.
Oh, okay, I see. So the reward model is like a quality control expert taking the LLM's raw output and polishing it up.
Yeah, that's a great way to put it. It's nudging the LLM to produce responses that are more helpful, more accurate, or whatever we want to prioritize.
So it's like training the LLM to give us the best possible search results every time.
Exactly. And you know what's really cool? Some of those fancy LLM techniques you might have heard of, things like best event sampling or majority voting.
Yeah.
They're basically just different re-ranker configurations, different ways of refining that final output, just like in information retrieval.
So we're really seeing these strong parallels between how LLMs work and how information retrieval systems work. I'm starting to see LLMs in a whole new light.
Me too. It's like we're decoding their secret language. But wait, there's more. What about when we train these LLMs on massive amounts of data?
Yeah, that seems like a whole other ballgame. How does that connect to the world of information retrieval?
Well, that's where supervised fine-tuning, or SFT, comes in. And guess what? It has a surprising connection to direct retriever optimization in ER.
Cool. You're going to have to break that down for me. Direct retriever optimization.
It's basically how we train those information retrieval systems to find the right document for a query. And SFT for LLMs, turns out it's incredibly similar.
So when we feed an LLM a massive data set of examples, it's like we're training a search engine to be super accurate.
Exactly. Both techniques use a method called contrastive learning with something called info-NC loss.
Info-NC loss. Sounds intense.
It's a bit technical, but basically it means we're trying to maximize the probability of finding the correct response or document given a specific prompt or query.
Okay, so we're optimizing for accuracy, both in LLMs and in information retrieval systems. But there's one thing that's been bugging me. With those huge data sets used for training IR systems, don't they have to make estimations because there's just so much data?
You're right, they do. But here's the kicker. LLMs, because of how they're built, can actually process the entire vocabulary during SFT. So their training is much more complete in that sense.
Ah, so that's one reason why SFT is so powerful for LLMs. It's like they get a supercharged version of retriever training because they can handle all that information.
Precisely. And it doesn't stop there. Remember those reward models we talked about, those re-rankers?
Yeah, the quality control expert.
Well, when we use those reward models to further refine an LLM through something called preference optimization, it actually mirrors something called distilling knowledge from a re-ranker into a retriever.
Hold on, distilling knowledge. That sounds pretty high level.
Think of it like this. Imagine a junior librarian, the retriever, learning from a senior expert, the re-ranker, about which books are truly the best fits for certain requests.
Okay, I'm starting to get the analogy. So we're basically teaching the LLM to be more discerning in its choices, to internalize the wisdom of that reward model.
Exactly. But here's a crucial difference. Preference optimization can actually add new information to the LLM. Things like stylistic preferences or safety guidelines that weren't necessarily in the initial training data.
So we're not just refining the LLM's existing knowledge, we're actually expanding its capabilities and shaping its behavior in new ways.
You got it. And that's what makes the research we're diving into so exciting. The authors proposed this brand new technique called LarPO LLM alignment as retriever preference optimization.
LarP. All right, I'm all ears. What makes this technique so special?
Well, it takes all these IR principles we've been talking about and leverages them for better LLM alignment. It's got three key elements that really set it apart: optimization objectives, hard negatives, and candidate list construction.
Okay, I'm definitely intrigued. Let's break those down one by one, starting with those optimization objectives. What are those all about?
Well, you can think of them as the guiding principles for how the model learns from the data. LarPO explores different objectives inspired by IR, specifically something called list-wise ranking.
List-wise ranking. How's that different from the usual way of doing things?
It's all about taking a more holistic view. Instead of just comparing pairs of responses, list-wise ranking considers the overall quality of the entire response list. And it turns out this approach can be much more effective.
So it's not just about picking a winner, it's about making sure all the finalists are top-notch.
You got it. Now, we're also going to talk about those hard negatives, those challenging examples that really push the LLM to think harder and how they play a crucial role in the training process. But we'll save that deep dive for the next part of our exploration. Stay tuned.
All right, welcome back. Last time, we were really starting to get into the weeds with those connections between LLMs and information retrieval. I feel like we're uncovering some hidden code that unlocks a deeper understanding of these LLMs.
I know what you mean. It's a bit like finding a secret passageway in a library, leading to a whole new section we never knew existed.
Exactly. And I'm eager to keep exploring. Remember how we touched on this idea of iterative learning? How it's kind of like climbing a spiral staircase of knowledge?
Yeah, it's a fascinating concept.
Well, I'm really curious to unpack that more. How does that iterative process actually work when we're training these LLMs?
All right, so picture this. In traditional information retrieval, you train a retriever. But then you can use its results to create new training data.
So the retriever is almost teaching itself to be better, kind of a feedback loop.
Exactly. And this approach has already been showing some promising results in LLM research. Techniques like iterative preference optimization are showing we can boost performance over time with this feedback loop.
That's pretty cool, but hold on. If we're constantly feeding the LLM's own output back into its training, wouldn't that risk amplifying any biases or limitations it already has? It seems like we could end up in an echo chamber.
You're absolutely right to point that out. It's a valid concern. That's where those IR principles we've been talking about become even more crucial, especially those hard negatives.
Oh, right. Those extra challenging examples that really push the LLM to think harder. It's like hitting the gym and adding more weight each time.
Exactly. When we're doing this iterative learning with LLMs, incorporating those hard negatives is essential to avoid getting stuck in that echo chamber you mentioned. By showing the model examples that are tricky to classify or rank, we're forcing it to confront its weaknesses.
It's like saying, hey, LLM, don't get complacent with the easy stuff. Here's a real brain teaser to keep you on your toes.
That's a great way to put it. It helps the LLM develop more nuanced and robust representations of the data, less likely to fall into those echo chambers.
Okay, so iterative learning, hard negatives, check and check. What other gems from the world of IR can we apply to LLM training? What else could we steal from the librarians, so to speak?
Well, remember LarPO, the new technique we talked about last time?
Oh, yeah, LarPO, the one that was blowing all the other methods out of the water on those benchmark tests.
Exactly. LarPO really tackles these aspects of iterative LLM training head-on. It starts by exploring different optimization objectives. Think of these as the guiding principles for how the model learns from the data.
Right, so like different training philosophies.
Yeah, and what they found is that objectives inspired by IR, specifically list-wise ranking, produce significantly better results than traditional methods that only compare pairs of responses.
So instead of just pitting two responses against each other, LarPO looks at the whole list and aims for a set of responses that are all high quality.
You got it. It's like judging a figure skating competition. You're not just looking for the one skater who nails a triple axel. You want a group of finalists who all deliver incredible performances.
Makes sense. So LarPO is all about setting a higher bar. What about those hard negatives? How does it handle those?
Well, LarPO is not afraid of a good challenge. It actually embraces the power of hard negatives by selecting responses that are intentionally difficult for the LLM to rank or classify. You know how we talked about the temperature parameter in LLMs?
Right, that's the dial that controls how creative or how random the LLM gets. High temperature, things get wild and unpredictable. Low temperature, things are more focused.
Exactly. LarPO uses that temperature parameter to fine-tune the difficulty level of those negative examples.
So if the LLM gets too comfortable with the easy stuff, LarPO cranks up the temperature and throws in some curveballs to keep it on its toes.
Yeah, and those curveballs force the LLM to sharpen its decision-making skills. Helps it pick up on those subtle nuances in language.
Okay, so LarPO is all about pushing those LLMs to their limits. But there's one more piece of the puzzle, right?
Okay.
The candidate list construction.
Right. This is where things get really strategic. Remember how we talked about inclusivity and memorization being so important when putting together that list?
Yeah, it's like we're building this diverse library for the LLM to draw from. We want a wide range of books, and we also want to remember those hidden gems we stumbled upon in the past.
Precisely. And LarPO takes both of those principles to heart. They found that having a larger, more inclusive candidate list and even weaving in responses from previous iterations significantly improved the LLM's alignment.
So we're giving it a wider perspective and a longer memory. Instead of being stuck in the present, it can draw on a much richer pool of knowledge.
Exactly. And that ability to learn from both current and past responses is a key factor in how well LarPO works. Okay, now switching gears a bit. We've delved deep into iterative learning, those hard negatives, and all the strategies behind building an effective candidate list.
It's been a wild ride. But now I'm curious, how do we actually measure the effectiveness of all these IR-inspired techniques? What kind of yardstick are we using to evaluate these LLMs?
That's a great question, because now we're not just assessing the LLM's ability to generate text that sounds good, we're evaluating its ability to function as a top-notch information retrieval system.
So we're putting our IR hats back on and treating the LLM like a retriever.
Precisely. And one of the key metrics we use in this context is recall it in.
Okay, recall it N. Remind me again, what does that tell us and why is it so important?
Okay, so imagine you ask an LLM a question. Recall at N measures how often the correct answer pops up within the top N responses generated by the model. Let's say we set N to 10. We're checking whether the LLM can retrieve the right information within its top 10 responses.
So it's a test of the LLM's accuracy.
Yeah.
Can it surface the most useful information quickly and consistently?
You got it. And what's fascinating is that when researchers actually evaluated LLMs using this recall at N metric, the results were incredibly similar to how traditional retrievers perform in the IR world.
Wait, so LLMs, even with all their fancy language generation skills, are actually behaving a lot like the information retrieval systems we use every day.
Exactly. And that realization is huge because it means we can use all this knowledge and all these techniques from the field of information retrieval to improve and understand LLMs even better.
Wow, mind-blowing. Every time we peel back another layer of this connection between LLMs and IR, we uncover these amazing parallels. It's like these two fields were meant to meet.
I know, right? It's like they're completing each other. And honestly, we're just scratching the surface here. There's so much more to explore.
All right, my brain is officially full for now. But we've got one more exciting part to go in this epic deep dive into LLMs through the lens of information retrieval.
Oh yeah, you won't want to miss this. In the final part, we're going to get into the nitty-gritty of how researchers are putting these IR-inspired techniques into practice. We'll explore specific examples, analyze the results, and see what this all means for the future of LLM alignment. Stay tuned.
Okay, we're back. and ready to wrap up this incredible journey into the world of LLMs through the lens of information retrieval. It's been a wild ride, but I feel like we've uncovered some seriously powerful insights.
Yeah, it's amazing how much we can learn about these cutting-edge language models by looking at them from this unexpected angle.
Absolutely. So in this final part, I'm super curious to see how researchers are actually putting all these IR-inspired techniques into practice. Did they run any experiments to test out these ideas?
Oh yeah, they definitely did. They wanted to isolate the impact of each of those key IR principles we've been talking about, to see how much they really move the needle when it comes to LLM performance.
So they were putting those theories to the test. What kind of experiments did they do?
Well, they ran a bunch of different experiments, but let's start with those optimization objectives. They wanted to see which ones actually led to the best LLM performance. Remember we talked about pairwise ranking, contrastive ranking, and then those listwise methods like lambda rank and listmle.
Right, those listwise methods were the ones that took a more holistic approach, looking at the entire response list instead of just individual pairs. It was like judging a figure skating competition, where you're looking for a group of amazing finalists, not just one winner.
Exactly. So they trained a couple of different LLMs, Gemma 22 and Mistral 7 both on the same dataset, ultrafeedback. And they ran these training experiments for 3 iterations using different optimization objectives each time.
Okay, so each objective got its chance to shine.
Yeah.
And what happened? Did those listwise objectives live up to the hype?
They totally did. Both listmle and lambda rank consistently outperformed the pairwise and contrastive methods across 2 different benchmarks, alpaca-eval 2 and mixeval.
Wow, so it seems like considering the whole response list, not just those individual comparisons, makes a big difference.
It does. It's like looking at the big picture instead of getting lost in the details.
Okay, score 1 for the IR-inspired approaches. What about those hard negatives? Did they look into those as well?
Yeah, they wanted to see how much of an impact those hard negatives really had on the final performance of the LLM. So they ran this experiment using the Mistral model on the GSM-8K dataset.
The math problem dataset, right?
Yep, that's the one. And guess what? They found that the harder the negative examples were, the better the final LLM performed. It's like giving those LLMs a good mental workout. The more challenging the exercises, the stronger they become.
So it really is like hitting the gym and lifting heavier weights. It's all about pushing those limits. And didn't they also find that the temperature parameter had something to do with how difficult those negative examples were?
They did. Basically, they found that within a certain range, lower temperatures tend to produce harder negative examples, because at lower temperatures, the LLM's responses become less random and more focused, so they can be trickier to distinguish.
Ah, so there's this sweet spot for the temperature. Not too hot, not too cold, just right, to create those challenging but not impossible negative examples.
Yeah, exactly. Now, the last thing they looked at was candidate list construction. Remember how we talked about inclusivity and memorization?
Right. It's like creating that diverse library for the LLM with a wide range of books and a good memory for those hidden gems.
Well, they tested this out on the Gemma 2 model, and they found that the larger the candidate list, the better the LLM performed. It's like having a wider range of ingredients to choose from when you're cooking. The more options you have, the more likely you are to create something amazing.
It makes sense. More options, more possibilities, more chances to refine those decisions. And what about memorization? Did remembering those past responses make a difference?
Oh, absolutely. When they incorporated responses from previous iterations into that candidate list, they saw some pretty significant performance gains. It's like the LLM can learn from its mistakes and build on its successes over time.
It's almost like it has this secret journal where it records all its past attempts, and then it uses that journal to constantly get better and better.
Yeah.
So we've covered a lot of ground here. What's the main takeaway? What does all this research tell us about the future of LLMs?
Well, I think the big takeaway is that applying those IR principles can make a real difference when it comes to developing these LLMs. We can nudge them to be more accurate, more relevant, and more aligned with our goals by using techniques like listwise ranking, incorporating those hard negatives, and being really thoughtful about how we construct those candidate lists.
It's like we're unlocking a secret code,
Yeah.
finding a way to translate the wisdom of information retrieval into the language of LLMs.
Exactly. And this opens up so many exciting possibilities.
It really does. It feels like we're just scratching the surface here, and there's so much more to discover. But we have to wrap up for today. Any final thoughts you want to leave our listeners with?
Yeah, just something to ponder. If we could create the perfect, hard, negative examples for these LLMs, examples that really challenge their assumptions and force them to confront their biases, what incredible breakthroughs might be possible? It's a fascinating question to think about.
It really is. And it reminds us that we're still just at the beginning of this incredible journey of understanding LLMs. So to all our listeners out there, keep exploring, keep questioning, and keep pushing the boundaries of what's possible.
Couldn't have said it better myself.
Thanks for joining us on this deep dive, everyone. Until next time, keep learning and keep innovating.